let's see if we can learn about this topic. Okay, so we want, here's the idea. Let's say that we're going to look now at linear maps that are not onto. We want to have a measure. We want to have some simple measure of whether a map is onto or not. Okay, so I could take, let's say, a map H from X, Y, Z. Let's say it's to X plus Y and X plus Z from R3 to R2. So how do I know if this map is onto or not? Well, what we're going to do is we're going to look at what we're going to introduce. First, the idea of a subspace well, let's not. Let me just go ahead with something that's going to be. Let's consider the image of all these vectors here. That is, let's say this is the image. Let's look at the set of all the vectors of this form. Okay, so we're going to call this set here is all the vectors that are of this form, right? Such that X, Y, and Z are any real numbers. So as I let X, Y, and Z in the domain go over everything, I want to look at all the vectors that are the images. This is an image space, right? It's a space or set of images. So R here is called this set. It's going to turn out to be a vector space. This set here, R, is called the range space. The range space of the domain V, because I take any vectors in the domain and I get a set of vectors here. So let me draw a picture. Here's the vector space V. And here's the vector space W. Now, if the map here that goes between them here, H, was onto this, then W would be the range space. But let's say that V maps into a smaller space. I don't get all the vectors, right? Because then it wouldn't be onto, right? So if it's not onto, there is some set of vectors that is the target, right? This space R is all the images. All the images under H. So I take all the vectors V here. Every point here maps into here. Right? Because I've taken, this is all the images up here. So the range space is all the images. So it's you say it's the image of the domain, right? So the range space is just all of these things. Well, it turns out that you notice that this is, I can write this. This is a free linear combination with X, Y, and Z. So I could write this as X times something plus Y times something plus Z times something. I can always write R as a span. So the range R, the range space is a subset of W. And because it's a span, right, it is a vector space. So the range space is a vector space. Okay? So the range space is a vector space. And because it's a vector space, it has a basis, right? Because it is a vector space, it has a basis. So it has a dimension. So it has a dimension, a number of vectors in that basis. So we give a name to the dimension of the range space equals the rank of the map. So here let's say you wanted to, so a lot of the problems in the assignment ask you to, you're given a map and you're asked to find the range space, which means looking at this space and writing this as a span, because then you've determined, so you basically want to write the range space as a span, find a basis for it, because that shows you what it is. That sort of is the standard way. This is sort of like a solution set of a homogeneous linear system, or there is a homogeneous linear system for which this is the solution. Okay, and it turns out then that the problem that you're asked is find the range space and find the rank of the map. So finding the rank of the map means finding the dimension of the range space. So I'd look up here's R, and I'd say that R here equals X plus Y, X plus Z, such that X, Y, and Z are members of R. And then I'd write that as a span, which again, the trick is you let Y and Z be 0 and say that's X times 1, we'll factor out the X there. Then you pretend the other two variables are 0, X and Z, and this would be Y1, 0. Then do the same thing with Z, pretending X and Y are 0, and you'd end up with 0, 1, such that X, Y, and Z are members of R, right? This is what you've done with solutions of linear systems from the first assignment. You've taken a solution set here. This came from sort of some form like this, in which you had to write the vectors here had variables in them, and you had to factor out the vectors, write them as a set, as some linear combination of vectors with constant components. Okay, so now we've written R as a span, and so we have a candidate basis, these three vectors. But you notice here, this is sort of trivial to notice that 1, 1 equals 1, 0 plus 0, 1. So this is dependent. So a vector space with a dependent vector, you can remove the dependent vector. So without changing the span. So R equals Y times 1, 0 plus Z times 0, 1, such that Y and Z are members of R. Now, those are clearly linearly independent. Therefore, the dimension of R equals 2. Therefore, the rank of H, the map H, equals 2. So the dimension of the range space equals the rank of the map. That's the definition. That's what we mean by the rank of the map H is the dimension of the range space. So this is how you find. If you're given a map, like let's go straight to the assignment and show you this is a task that's concrete for you to do. In assignment 5, like here's a map. Let me see if there's a map from one vector space to another. Ask you, what's the range space? What's the rank? Here's one from R3 to R2. What's the range space? What's the rank? Here's a linear map from this vector, from this vector space to R. What's the range space in the map? Here's one where's well, later on we're going to bring in matrices, but there's all kinds of problems here finding the range space and the rank. So so this shows you how to do half of those kind of problems. Okay.